We are about midway through this series on mechanics, so we thought it would be a good idea to take a little break, summarize what we've done so far, and outline what remains in store. We started more than a year ago with this table, the table of what we called standard mechanical quantities. Mass, density, force, energy, pressure, viscosity, all these terms fill the pages of textbooks and papers. This table tries to make sense of their relative dimensions. Each mechanical quantity in this table is what we also called a mass-carrying quantity, because they all have a dimension of mass and some combination of the dimensions of space and time. M, L, and T, the three dimensions of mechanics. The exponents x and y of the space and time dimensions respectively give the horizontal and vertical positions on this chart. Once we know the dimensions of a quantity, we can put it on the map. This is what we did for the first time 4 years ago on the back of an envelope. Then, with the Inside of Time, it took us just a couple of hours to put this map together, but it required centuries to be explored. From antiquity to the Middle Ages, only a few spots were known. The Renaissance brought many discoveries, and the last few centuries have filled a lot of gaps. Nevertheless, the exploration continues, and this chart is but a sketch of a much broader universe. We are impatient to go on exploring, but before getting pulled outside the map, we've got to better appreciate what we already have, and why generations of thinkers have sailed these waters. What is so special about these mechanical quantities? Why do they have this peculiar dimensional structure? Because they all belong to the same paradigm, to the same way of understanding this trinity of dimensions. Mechanics admits multiple paradigms, but this entire series is dedicated to one in particular, the dynamical paradigm. Within this approach to mechanics, mass is called upon to conceptualize space, time, and their intersection, motion. Undoubtedly, this way of thinking about nature drove the development of the mechanical philosophy and motivated the definition of these mechanical or mass-carrying quantities. The dimension of mass clearly has a special role in these quantities, and for reasons that we can now better appreciate. Within the dynamical paradigm on mechanics, the things we see, measure, and seek to explain are within what we've called the kinematic plane. It is this plane that is directly accessible to measurements of length, times, and their combination. In the dynamical paradigm, what we see on this plane is understood as influenced by a higher dimension, the dimension of mass. This series chronicles the incursion of this additional foreign dimension, and in doing so it lays the foundation for a dimensional approach to mechanics. The building blocks of this approach are mechanical duos, pairs of mechanical quantities. Initially, the goal of the dynamical paradigm is to understand what is seen in the kinematic plane, and so to compute kinematic quantities. Here, kinematic is defined rather generously to include geometric quantities that are purely spatial, and also to include temporal quantities. Whether we want to explain a size, a frequency, a speed, an acceleration, a diffusivity, or a more exotic metric of motion, any combination of spatiotemporal dimensions can be understood as a ratio of mechanical quantities, the kinematic outcome of an interaction between a pair of quantities from a higher dimension. This is the reason why mechanical quantities all have the same dimension of mass, because this dimension is meant to cancel out when taking ratios of pairs. Mathematically, this expression is almost trivial. Divide a mechanical quantity by another one, and what you'll get is purely kinematic. The kinematic exponents are now expressed as differences. The scope of this simple idea is immense. What we see in the kinematic plane as size, duration, or motion can be understood from another plane, a mechanical plane. A point on that plane corresponds to a mechanical quantity, with dimensions set by the coordinates of that point. A single quantity, a single point on that plane, has no hope of reaching the kinematic plane. But if we consider 2 points, 2 quantities, then taking their ratio bridges the divide. The table of standard mechanical quantities records the recurring players, the factors most often used in the decomposition of kinematic quantities in mechanical terms. The ratio of a pair of mechanical quantity is a kinematic quantity. That's it really. The first 8 episodes of this series are basically rearranging this formula in different ways, looking at it from different angles, and showcasing its vast range of applicability. In episode 2, we considered horizontal pairs, sharing the same time dimension. In that case, the kinematic outcome is purely spatial. Depending on the exponent x1 and x2, it could be a length, an area, a volume, but it could even have dimensions that are apparently harder to interpret geometrically. Nevertheless, nature has no trouble at all finding ways to express this scaling. For instance, we saw that the radius of many types of craters can be expressed as a balance between the energy E generating the crater, that of an explosion or impact, and the weight density psi of the lifted ground material. A length scale such as this one, based on a pair of mechanical quantity, is what we called a simple length. We saw a bunch of examples, many in episode 2, and a few more since. Even if we restrict ourselves to the standard mechanical quantities in the table, more than 60 different simple lengths can be built, each underlying a different kind of mechanical balance leading to a purely geometric outcome. We'll see more examples in future videos, but we invite you to explore on your own. In episode 3, we used the same formula again, but this time focusing on quantities aligned vertically. No more spatial dimension, this gave us simple times. Here again we saw a wide range of examples where time, frequency, or duration could be expressed from a ratio of 2 mechanical factors. Again, these examples are but a small fraction of the possible simple times, and you are invited to find others on your own. In episode 4, we gave another special case of this formula, a first encounter with motion, when 2 quantities are on a diagonal of slope -1. In that case, the gap in the spatial dimension is the same as the gap in the temporal dimensions, and the resulting kinematic quantity is the power of a speed. We could thus define simple speeds, for which we also found multiple examples. And there are a lot more. After these introductory episodes, we could finally address the general case in episode 5. Length, times, speeds are instructive spatial cases, but generally the ratio of an arbitrary pair can mix space and time in many ways. In a few more cases, the produced kinematic quantities has a standard name, but usually it does not. We've seen, however, that many different kinds of these kinematic quantities have been observed in the past few centuries. In some cases, their existence can be evidenced by recording the relationship between a measured variable length d and a variable time t, which provide the dimensions of length and time in the kinematic plane. Then, with these variables, the relative dimensions of an arbitrary pair in the mechanical plane is reflected by a power law connecting the 2 variables. That is a straight line in log scale, what we also called a regime. This regime is given directly from the pair of mechanical quantities. The slope of the power law in the kinematic plane reflects the link connecting the 2 mechanical quantities. And this is not a figure of speech. We go from the slope in the mechanical plane to the slope in the kinematic plane by performing a vertical flip. So if the slope is ascending in the mechanical plane, then it decreases in the kinematic plane. The size is shrinking, and vice versa. So far, we've mostly favored this growing case. We saw many examples, including a famous one for explosions due to Taylor, a diffusive regime due to Rayleigh, found in the pinching, coalescence, and spreading of some droplets and bubbles. For pinching, the time is the duration before pinch-off, so the dynamics proceed from right to left. Still with bubbles and drops, we saw a steeper regime, as the two mechanical factors are getting closer to one another in the mechanical plane, the slope of the parallel increases. The regimes at constant speed, or uniformly accelerated, are not more important than the others. The simple length is just a regime of slope 0, and the simple time is of infinite slope. The force and the mass. It is the pair that started this whole mechanical way of thinking about kinematics. A pair that leads to a uniformly accelerated kind of motion. It is no more fundamental than any other pair, but it's been the template for all. We saw in episode 6 that in any regime, the mechanical factor in the numerator is the quantity on the rightmost side of the mechanical plane. We've been calling it the impelling factor. In the denominator is the impeding factor. Once the mechanical quantities are known, what drives and what resists motion is known. If there is a regime where Q1 drives and Q2 resists, the regime where Q2 drives and Q1 resists simply does not exist. Since episode 6, we've often symbolized this by labeling a regime by the pair of associated mechanical quantities. The order of the elements of this set does not matter. The roles are assigned by the dimensions. Impelling and impeding. These roles are not absolute. They depend on the relative positions of the mechanical quantities. For instance, the mass may be impeding when facing a force, in which case it is said to be inertial, but for orbits it can drive motion. It is gravitational. In this context, the size is that of an orbit, the time is the period of revolution, the mass is that of the central body, and the upside-down g, what we called gravity, is basically the inverse of the gravitational constant. This way it is a proper mass-carrying quantity. The scaling connecting size and time is Kepler's law, with mechanical factors found by Newton. This is the most famous example showing how a stereotypical resisting factor can turn out to be driving things when paired with the right quantity. We also talked about boundary layers, where paired with density, viscosity, despite its name, is the impelling factor. In other situations, like the coalescence of bubbles in viscous outer fluids, or with the spreading of cellular aggregates, viscosity recovers its usual impeding role. Quantities on the right of this table tend to be more often driving than resisting, but we have to be careful not to be misled by their historical names, relics of a time where this relativity of the impelling and impeding roles was not yet understood. A mass, a viscosity, or a friction, despite their names, these quantities can very well be promoting motion in some situations. This way of expressing the relationship between a pair of mechanical quantities as a scaling law between a length and a time is quite useful, quite visual in many cases, but it is just one perspective among others. We called it the canonical perspective, but we saw in episode 7 that we can always translate a scaling to any perspective we may choose. The general formula is dimensional. In some cases, the dimension of length and time can directly be expressed from a variable distance and a variable time. But in some situations, it might be more convenient to use different variables, like a wave number and a frequency. With such slight change in perspective, the transition is fairly straightforward, and so we saw, for instance, that the 2/3 scaling seen for pinching droplets in the canonical perspective corresponds to the same physics as that seen in the dispersion relation of capillary ripples. The mechanical pair is the same, an impelling surface tension and an impeding density. 3/2 rather than 2/3, the exponent is different simply due to our switch in perspective. In some cases, the translation is a bit more involved, because the variables are more complicated. For instance, we saw that Kolmogorov's famous -5/3 spectrum, commonly discussed in turbulent studies, corresponds to a 3/2 spectrum in the canonical perspective, connected to the dynamics of coherent structures, impelled by the power density pi, and impaired by the density of the fluid ρ. Different perspectives offer complementary approaches on the same physics. The physics is set by the pair of mechanical quantities, and the variables offer different ways to group the kinematic dimensions. We saw in episode 8 that for any pair of mechanical quantities, we can actually choose the whole kinematic outcome of the ratio as dimensions of a single variable. Since in this paradigm the mechanical quantities are constant parameters, their ratio must also be constant, so we provocatively called the corresponding kinematic quantity the constant variable of the regime, in analogy with the constant acceleration characterizing free falls. For any pair, when this kinematic contribution is chosen as one of the axes, then the regime becomes flat, orthogonal to that axis. For this reason, we call this privileged perspective the right angle on the regime. In this perspective, the other axis can be any variable other than the constant variable, or powers of it. No matter what we choose, the dynamics are invariant along that axis, which becomes largely irrelevant, just like time was, for instance, irrelevant when considering simple length. Indeed, from this spatial perspective, the regime is simply given by the equation connecting our single constant variable and its mechanical decomposition. Whereas the horizontal axis is completely indeterminate, the vertical axis acquires a natural unit, which is none other than the mechanical ratio. We called such a unit objective because it does not depend on international, national, or personal preferences. It is set by the physics of the phenomenon at play. We saw that measuring our constant variable with this objective unit was the same as defining a simple dimensionless number. The constant variable in objective units is the simple dimensionless number of the regime. For any pair, there is an associated dimensionless number. We discussed a few pairs built from the standard quantities and for which the dimensionless numbers have names, like the Reynolds number built from viscosity and density, and where the constant variable is usually written in terms of a length and speed. We also saw the Weber number combining surface tension and density, or the Froude combining force density and density, the Bond comparing force density and surface tension, or the Mach number for the stress and density pair. In some cases, like this one, we saw that the traditional definition differs from the general formula by some power. Any dimensionless number is indeed defined modulo an overall power, vestige of historical circumstances. These slight variations in definition can be a bit annoying in some cases, but they should not distract us from the essential. Any pair of mechanical quantities is associated to a power law. In the canonical perspective, the slope of this regime is a direct reflection of the positions of the mechanical factors. Different values of the mechanical quantities lead to lines with the same slope but different prefactors. The higher the value of the impelling factor, the higher the line. The higher the value of the impeding factor, the lower the line. With these variables and their arbitrary units, the dynamics on each line look superficially distinct from one another, but it is only an illusion, consequence of our poor choice of perspective. Once we select the right angle, the ordinate of each line is set by the value of the mechanical ratio in that case. And if we use this ratio as our objective unit, all data collapse on the same master curve. This introduction to objective units concluded our tour of the connection between pairs of mechanical quantities and their effects in the kinematic plane. For a more in-depth summary of these first 8 episodes, you are invited to check our review about these fascinating dynamic duos. There is still a lot to say about this simple formula, and involving a third mechanical quantity can actually help us understand pairs more intimately. So starting with episode 9, we introduce mechanical trios. Two cases must be distinguished, whether the three quantities are aligned or not in the mechanical plane. So far, we focused on the non-aligned case. We proceeded step by step, starting with what we knew. In episode 9, we initially placed ourselves in the canonical perspective. We acknowledged that in any trio, 3 pairs could be found, and so a regime could be drawn for every pair. The 3 regimes intersect at a common point, a simple consequence of trigonometry. We call such spacetime point an event. We saw that the coordinates of such event could be derived easily by equating any 2 regimes or directly from dimensional analysis. The time and length of the intersection are the only time and length depending solely on the 3 mechanical factors. So we introduced indices to recall the mechanical trio, the order of the indices being insignificant. We saw a few examples of these events. For instance, we discussed the trio of energy, mass, and density, useful to understand the early dynamics of detonations. The 5th episode of the explosion series is also dedicated to this event. We also talked about energy, density, and bulk modulus in episode 10 and in the 4th episode on explosions. The slopes are the same, but the simple length is now built from the energy and the modulus, and the simple speed is the speed of sound. The coordinates of the event change accordingly. In episode 9, we also saw the unsorted point at the crossroad of surface tension, density, and viscosity, useful for the study of spreading, pinching, and coalescence of bubbles and droplets. We also saw Kolmogorov's point for the microscales of turbulence, governed by density, viscosity, and power density, and the event at the crossover between waves and ripples, governed by density, surface tension, and force density. For any event, we saw that the coordinates of the point of intersection could be derived from any perspective. For instance, in this case, we saw that we could get the point of intersection in the dispersion relation. In any case, when we have 3 non-aligned mechanical quantities, we get a single point of intersection, and this event provides a turning point for the dynamics. We've barely begun to explore this concept, yet we've already caught a glimpse of its significance. Although experiments restricted to a small range may only evidence a single power law, where only 2 mechanical quantities are at play, if tracked for long enough, the influence of an additional quantity will eventually be felt and the dynamics will change. The first regime is here impelled by a quantity Q1 and impeded by Q2, which is indeed on its left in the mechanical plane. After the intersection, the dynamics are driven by the interplay between Q1 and a new quantity Q3. Because Q1 is still on the right, it continues to impel motion, but Q3 is the new impeding factor, supplanting Q2. So in this particular example, the transition in the kinematic plane reflects a switch in impeding factor. What drives the dynamics remains the same, but what resists changes from Q2 at short time to Q3 at longer times. The important is that a mechanical quantity is shared between the 2 regimes. What we saw in episode 9, 10, and 11 is that if 2 intersecting regimes have a mechanical quantity in common, then we get a 3rd regime for free, corresponding to the 3rd pair of the trio. This 3rd regime offers different paths around the event, the common point of intersection between the 3 regimes. At this event, as we saw, the impeding factor can switch, but other paths are possible. For instance, here, the impeding factor remains the same, Q3, but the impelling factor switches from Q2 to Q1. A 3rd possibility is that the impeding factor of the first regime, Q2, becomes the impelling factor of the 2nd regime. We saw examples of all of these kinds of turns at the event, but we did not yet find a way to know in advance which path to expect. We even encountered cases where some experiments saw dynamics along one path, while others saw a different path in parallel. We'll definitely have to study this path selection in more detail in the future. What we saw already in episode 10 and 11 is how a proper mechanization of these turning points offers ways to unify apparently distinct kinds of dynamics, corresponding to different paths around the same event. The literature is full of what we called pseudo-events, mechanically incomplete intersections, where only one regime is expressed from a pair of mechanical quantities, but the rest involves kinematic constants. For instance, we saw that if we introduce an adduct length L, then any additional parallel intersecting the first at this coordinate can be expressed by borrowing the mechanical factors of the first parallel. We saw this with explosions, with low viscosity and high viscosity drops and bubbles, and even with the famous crossover between terrestrial and extraterrestrial gravitation. Any scaling that looks like this, or more generally like this, where k is any kinematic constant, a length, a time, a speed, anything depending solely on space and time, any scaling like this is mechanically incomplete. The impaling and impeding factors cannot be clearly identified because of the unfactorized kinematic constant. A scaling like this is what some have called a cell similarity of the second or 1.5 kind. A scaling written in this way cannot be derived by dimensional analysis alone. There are just too many parameters to know what the exponent alpha, beta, and gamma should be. For this reason, these scalings are often exhibited as evidence of the limitations of the method of dimensional analysis. However, we've seen that these scalings only witness our own shortcomings, or inability to identify additional mechanical factors underneath their kinematic disguise. Within a fully mechanical understanding of kinematics, these incomplete scalings are unacceptable. Whenever you encounter a scaling written like this, you must ask yourself, where is the missing mechanical factor? Can it be used as an impeding factor to cure the incomplete scaling paired with the first quantity, or paired with the second, or maybe as an impaling factor for the first or second quantity? Note that the regime could also be independent of the first two quantities, but in this case, we would need 4 rather than 3 mechanical quantities, a case we haven't yet talked about. Even if we restrict ourselves to 3 quantities, there are many possible mechanical models to replace the initially incomplete scaling. In the mechanical plane, the third quantity can be anywhere on either line of slope minus alpha, going through Q2 or through Q1. The search for this third mechanical quantity is what we provocatively called a game of mechanical bingo. We are just beginning to learn how to play this game, but we already know that if a mechanically incomplete scaling of exponent alpha intersects a mechanically complete scaling depending on a pair Q1 and Q2 at a point characterized by a constant value of any arbitrary kinematic parameter, k, then we can mechanize the incomplete scaling by introducing a third quantity Q3 anywhere on one of the 2 parallel lines of slope minus alpha in the mechanical plane. Where we put it depends on the usefulness of the third regime we get for free. If we want to obtain the regime of constant k, then Q3 can only be in 2 spots, either down here or up there. But we can also seek a completely different regime with any slope we want. The mechanical trio we eventually choose to regularize a pseudo-event may be constrained by traditions, those inscribed in the table of standard mechanical quantities, which restrict us to mechanical quantities with small integer coordinates. But ultimately, it must be compelled by experimental data. The third regime should be put to good use, to match observations. We'll have opportunities to talk more about these trios of mechanical quantities in future episodes, on how to select the right players to explain connected kinematic power laws. With pairs than with trios, our initial goal has been to find the right physics, the mechanical causes of the observed motions. Progressing toward that goal, we realized that the mechanical plane could also inform our choice of reference frame. In particular, we saw that with a trio of mechanical quantities producing an event, we could use the coordinates of that event as units of space and time. With pairs, we could only have an objective unit for the constant variable for a single axis. now we have objective units for both time and space, and so we can scale any axis we may choose. For instance, an experiment might only evidence the following path. In subjective units, the position of this broken line on the plot is set by the values of the underlying mechanical quantities. If these values are changed, then the broken line moves accordingly. With just a few experiments, the similarity between the curves is still quite clear. But if we multiply the measurements, we end up with a depressing mess. What we learn is that the apparent complexity of this plot is due to our poor choice of units. Here, our units are arbitrary, set constant for all experiments. They are set by an artificial point, having to do with our rules and regulations, not with the physics at play. The physics suggest a different point of reference. For each curve, the values of the mechanical parameters give us the coordinates of the point of intersection. In subjective units, these points occur at different locations. But these subjective units blur our vision. We see multiple events and many crisscrossing curves, where there is really only one. When represented in objective units, all dynamics pertaining to the same mechanical trio overlap. They fall on a master curve. Once we have three non-aligned mechanical quantities, we have an event, and this event provides an objective way to scale the kinematic plane. And this is basically where we are now. We're starting to see how efficient the dimensional approach to mechanics can be, but a lot of questions remain unanswered. We started with this formula, showing how the ratio of a pair of mechanical quantities gives a kinematic quantity. Since the beginning of this series, we've been mostly assuming that the mechanical quantities were known, and so the kinematics could be derived from them. But the equation works both ways, although the equality should not exactly be read in the same way. Reading from left to right, yes, the ratio of any pair of mechanical quantities is a kinematic quantity. Reading from right to left, any kinematic quantity can be decomposed into a pair of mechanical factors. For any given pair of mechanical quantities, we have a single associated kinematic quantity. For any kinematic quantity, we can always find a decomposition into a pair of mechanical quantities, but we do not have to. We've called length, times, or speeds, depending solely on two mechanical quantities, simple, because there are also lengths, times, and speed, and any kinematic quantities that are more complex and depend on more than two mechanical quantities. The coordinates of the events give us plenty of examples. For instance, the unsorted time and length depend on three rather than two mechanical quantities. Once we have three non-aligned mechanical quantities, we have units of both space and time, and so we can make up any kinematic quantity we may choose. For any trio, and so for any event, the three intersecting regimes correspond to the only cases where the associated kinematic quantity depends on two and not three mechanical factors. So any mechanical ratio is kinematic, and any kinematic quantity can be decomposed into a mechanical ratio, but not all are. What we also started to discuss is the fact that multiple mechanical ratios can be used to obtain the same kinematic quantity. The mechanical decomposition of a kinematic quantity is not unique. The mechanical factors we choose for a given regime should be informed by all the other regimes connected to it. The relationship between mechanics and kinematics is asymmetric, but a lot of work remains ahead in order to better grasp this asymmetry. We've planned about a dozen more episodes, which will greatly extend the scope of the dimensional methods that we are promoting on this channel. First, we'll have to discuss aligned trios, and we'll start with trios on the horizontal. In episode 2, we saw that a horizontal pair gave us a simple length. We'll now have three parallel lines. No more intersection, no more event. We invite you to start investigating on your own the relationships between these three lines, based on the relative positions of the mechanical quantities. This horizontally aligned case will allow a mechanical understanding of shape and structure, not just size. More generally, trios aligned along any direction will allow us to define a new kind of dimensionless number, depending solely on mechanical parameters, what we will call an index. The full potential of these indices will only be revealed by considering mechanical quartets, sets of 4 mechanical parameters. An introduction to this much richer playing field is already available in our mini-series on explosions, which was designed for this purpose. What we'll do in most of the remaining episodes of this mechanics series is to generalize the notions introduced in episodes 6, 7, and 8 of the explosion series. First, we'll define the concept of dynamical domain, connecting multiple events. Then we'll show how these domains can free us from the shackles of the subjective base 10 we've been using to count. Numbers, just like units, should be set by the mechanics at play. Finally, we'll move away from the kinematic plane and consider mechanical variables, which will eventually invite us to consider other kinds of mechanical paradigms. With 4 quantities, we have 6 pairs, and so 6 regimes. With this simple configuration in the mechanical plane, the 6 regimes produce 4 points where 3 lines meet, proper events just like the ones we've talked about. But with 4 mechanical players, we'll discover a new kind of event, where only 2 lines meet. The coordinates of events of this new kind depend on 4 rather than 3 mechanical quantities. These 6 lines and 5 points are linked by the same physics. They are the kinematic expression of the same quartet of mechanical players. A dynamical domain such as this one is an elementary building block of the kinematic plane, a patch of space-time connecting events that share a similar mechanical underpinning. Of course, the shape of this domain reflects the positions in the mechanical plane. Some variations in the mechanical plane only produce small changes on the shape of the domain. The topological structure remains the same. However, different topologies are possible, while the number of black and white events is different, while the web of intersecting regimes is qualitatively altered. The topology dictates the possible succession of events that we can observe in the dynamics, so figuring it out is critical. How many kinds of topologies are there? We'll have to understand which configuration of the mechanical plane leads to each kind of topology in the kinematic plane. For each domain, we will be able to define an index depending solely on the mechanical parameters, similar to what we will see for the 3 aligned quantities. The value of this index, smaller or larger than 1, will set the orientation of the domain. For instance, the domain might be oriented in this way if n is greater than 1, but it will be flipped if n becomes smaller than 1. You can already convince yourself of this duality on your own. These 2 orientations define 2 qualitatively different sets of dynamics on the domain. For instance, for explosions, we saw that the dichotomy separates detonations from deflagrations. Regardless of the value of the index, what we also saw in the explosion series is that although the coordinates of all events provide competing systems of units, they are all connected by the index. We can pick any event to define our units of space and time, and the coordinates of all the other events can be expressed as simple powers of the index, set by the relative positions in the mechanical plane. We saw then that a fully objective representation of the domain could be achieved by using the index as our radix, as the base of our log, instead of the conventional 10. The ramifications of such renormalization are far-reaching, but for now, all of this quartet ramble must feel quite arcane to you, especially if you've not watched the explosion series. Hopefully, in a few episodes, all this will be much clearer. Once we've sharpened all of these tools, we'll be able to address some things that we've been forced to sweep under the rug, like the scaling constants, the deltas, these numerical prefactors in each regime. So far, we've assumed that the quantities Q1 and Q2 provide a satisfying mechanical model of the kinematics, when delta is not far from one. With a radix defined mechanically, we'll be able to make this condition more rigorous. The mechanical radix will also allow us to better understand what happens in the vicinity of an event. The path followed by the dynamics. Why one path or another? And why some transitions are smooth rather than sharp. We've considered duos, trios, and we'll cover quartets. So the next logical step would be to talk about 5 mechanical quantities, isn't it? Well, we will not do that, not in this series. Even with what we'll have learned from 2, 3, and 4 mechanical players, we won't yet be ready for 5, because we'll first need to look back at our initial hypothesis, those of the dynamical paradigm. We'll have to evaluate how much of what we've built will resist a paradigm shift. Since episode 7, we know that tilting our perspective is rather harmless. A paradigm shift is a more serious business. This whole series is based on the assumption that the dimension of mass holds a privileged position, used to make sense of what is seen through kinematics. This dynamical outlook on mechanics has been very influential, but as said in the introduction, it is just one out of many possible paradigms. It is because we've elevated the dimension of mass above those of space and time that what we've called mechanical quantities have been so useful in building a language to understand kinematics as dynamics. To be more precise, so far we've only used a very small subset of mechanical quantities, the standard ones defined by the founding figures of mechanics. Why did they focus on mechanical quantities set by exponents that are small integers? As said earlier, the table of standard mechanical quantities records the recurring players, the factors most often found in the decomposition of kinematic quantities in mechanical terms, at least the one that we could find in the literature that we surveyed. We've probably missed some, and anyway, all of the empty spots on this table are not less deserving of a name than the one which have been favored by historical circumstances. But how far should we explore? What would be the use of such outlying quantities? Maybe you are seeing it already, but what we'll show is that going far away is the same as looking up close, between the lines and columns. The reason for this is again the simple but resourceful formula we started with. The correspondence between the mechanical and kinematic planes depends solely on the relative dimensions of the mechanical quantities. If you want to get ahead, just consider any regime, say in the canonical perspective, and ask yourself what would happen if the horizontal or vertical spacings in the mechanical plane become large. The only piece of mathematics you'll need to help you on your journey is this. A quantity raised to a vanishingly small power is barely different from unity. You should of course wonder about the base used for the log. This series started with this table, with the definition of mass-carrying quantities. We've gone a long way by solely considering standard mechanical quantities, with x and y small integers. We'll then be able to consider any integers, then any rationals, and eventually any real numbers, including irrationals leading to proper self-similarities of the second kind, a term from Baron Blatt mentioned in episode 10. But what about mechanical quantities in a more general sense, like those with a square exponent on the mass dimension, or any exponent for that matter? To some extent, we'll see that we can project these quantities back onto the initial mechanical plane by exponentiation. But at the end, we will have to reconcile with the fact that mechanics is more than a dialogue between two planes. In all generality, mechanics deals with 3 dimensions, m, l, and t, which do not provide a table, a plane, or a couple of planes, but a whole volume. The dynamical paradigms consider slicing this dimensional volume along the mass dimension. Different mechanical paradigms approach this space from different angles. By the end of this series, our hope is that you will share our conviction that a smart next step will be to consider an orthogonal paradigm, which will be the main topic of a future series on mechanics beyond dynamics. But let's not spoil all the fun. We hope you've enjoyed this little intermission. We'll return as soon as we can with episode 12, which will most likely be about aligned trios. Thanks a lot for watching.